Hi, I'm Maddie, and today I'll be explaining for you the three laws of motion, also known as Newton's laws of motion, as seen here. Now, before the 1600s, most scholars accepted the Greek philosopher Aristotle's theories of motion. And he thought that the speed of a falling object depended on its mass. Now, he thought that an object with a large mass would fall more quickly than an object with a small mass. Now, Galileo Galilei from Italy did not agree with this. He hypothesized that all objects fall at the same rate and that they accelerate as they fall. But Galileo could not measure the speed of falling objects because they fell too quickly to record. But today we can record this, and today we can use equipment and stuff to figure this out, but Galileo didn't have that kind of stuff back then. So he came up with a solution. He rolled balls of different masses down a ramp. So he used a ramp, and it allowed him to slow down an object's fall so he could measure it. Now, Sir Isaac Newton, who lived from 1642 to 1727, built on Galileo's ideas. He observed that a force could change an object's motion. So he explained that the motion of objects follows three basic principles, which we now call the three laws of motion, or Newton's laws of motion. So at first, Galileo's ideas were considered absurd because they challenged what people thought was true. However, Galileo's and Newton's experiments have been repeated many times with the same outcomes. So their hypotheses were accepted as correct. So scientific knowledge is indeed that the result of the contributions of many people over time. So, firstly, I'll be talking about Newton's first law of motion. So, Newton's first law states, an object at rest will remain at rest, and an object in motion will continue to move at the same speed in a straight line unless a force acts upon it. So, for the first law, which is also called the law of inertia, because inertia is a tendency of a still or moving object to resist changes in its motion. So the greater the mass of an object, the greater the force needed to overcome inertia and cause a change in the object's motion. So this is why that it may take 5 people to push a car while it takes just 1 person to push a bicycle. So here is my first example for the first law of motion, or the law of inertia. So today, I will be using a simple bouncy ball and myself. So what I will be doing is I will be showing you that the first law of motion is right. So let's say I set this bouncy ball down and it isn't moving anywhere. That's because I haven't touched it or an outside force hasn't moved it. But if it starts to roll, it will not stop rolling until an outside force acts upon it. So, if the bouncy ball is rolling, I can stop it, and I would be the outside force acting upon the bouncy ball. Now, the bouncy ball would be stopping because I, the outside force, have just acted upon it. So that is my first example. Now let's take, for example, this water bottle. Now, although it is empty, it will still work for my demonstration. So, if I drop the water bottle on the floor, it rolls away. Now, it doesn't stop rolling until it hits the side of the wall. Now, the wall is the outside force, and the water bottle is being stopped by that force. But if I just set it down like this, the water bottle will not move because it is flat on the bottom and the force has not done anything to it. So that is my second example for the first law of motion, also known as the law of inertia. Alrighty. So, for example, for the first law of motion, let's suppose, just suppose that a fast-moving test car crashes head-on into a barrier. The car crumples, slows down, then stops. This all happens in less than a second. but because of inertia, any test dummies that are not wearing seatbelts will continue to move forward at the same speed that the car was traveling. The test dummies may hit the windshield in front of them. But on the other hand, the test dummies that are wearing seatbelts are attached to the seats in the car. They slow down as the car slows down. So this is why we always buckle our seat when we're in the car. So if we get in a crash, we will not fly forward into the windshield. This is Newton's second law. It states, an object acted on by a net force will accelerate into the direction of the force. The object's acceleration equals the net force on the object divided by the object's mass. So, acceleration equals force divided by mass. But another way of stating this relationship is that the net force on an object is equal to the product of its mass and its acceleration. So, force times force equals mass times acceleration. So Newton's second law of motion shows how force, mass, and acceleration are related. An object's acceleration will change if either the force on the object or the object's mass changes. The law is often shown in two ways. So right here you can see, even though it's backwards, this shows acceleration equals force divided by mass, or force equals mass times acceleration. Now, that is a little bit about Newton's second law of motion, and this is my first example for Newton's second law of motion. So we have the picture here, even though it is backwards. So this says mass and acceleration. And this this is the net force on cart A, and this is cart A, and the net force is 60 newtons, and the cart is 30 kilograms. So remember, it's force divided by mass, it's acceleration. So you would do 60 newtons divided by 30 kilograms equals 2 meters per second per second. Now, the net force on cart B is also 60 newtons. And so it's 60 kilograms, so you would do 60 newtons divided by 60 kilograms, which equals 1 meter per second per second. So that was my first example, and as it says here, one grocery cart has twice the mass of the other. The same net force, which is 60 newtons, acts on both carts. But the cart with twice the mass has half the acceleration of the other cart. So, cart B has more mass in it because it's 60 kilograms, while cart A is 30 kilograms. So, cart B, he has twice the mass, but it has half the acceleration of cart A. Now, my second example involves two chairs. Alrighty, so here we go. Let's move this over a little bit. Okay. So, take these two chairs, for instance. Now, just like how we were saying about the grocery carts, let's say there are 30 newtons acting upon both of these chairs. And there is, let's say there's some magazines here and the TV remote. So this has more kilograms than this chair, which has nothing on it. So if you're doing force divided by mass is acceleration, you would do, let's say, let's say this chair is 10 newtons, 10 kilograms, so sorry. So you would do 30 newtons, since that is what is acting upon both of the chairs, divided by 10 kilograms, which equals 3. So this is 3 meters per second per second. Now, if you're doing it with this cart, this chair, you would simply do 30 newtons divided by 0 kilograms, which equals, I'm going to do it on the calculator anyway, which equals 0 newtons. So it would be 0 meters per second per second. So this chair, even though it has twice the mass of this chair, it has half the acceleration as this chair, because like I just showed you with the equations. Alrighty. So, on to Newton's third law of motion. Alright, Newton's third law states, for every action force exerted on an object, the object will exert an equal and opposite reaction force. So, one example could be, so I am pushing on the door. Now, as you see, it's not moving because the door is pushing back the same amount of force that I'm pushing on it. So, we're each pushing the same amount of force on each other, making the door not move. But let's say I was pushing less force than the door. Then the door would move this way because it's pushing more force than I'm pushing on it. But if I'm pushing more force than the door is pushing on me, the door would move that way because I am giving more force than the door. Now, another example is, as you can see in this picture, we have a swimmer, and she is pushing against a large mass of water. Now, the water is pushing back with an equal force, but on the swimmer's much smaller mass. So the net force accelerates the swimmer enough to overcome the friction and let her keep going. So basically what this is saying is that the swimmer is pushing on the water one way, and the water is pushing back on her in an equal way. But since the water has a much bigger mass, she will push through the water and continue swimming on. So that is my other example for Newton's third law of motion. So, let's see here. So, that is all today for what I will be showing you. So if you'd like to learn more, just come to Miss Kalana's class and follow up with us. Thanks. Bye.